Thank you for coming, Professor Voevodsky. Welcome to Nanyang Technical University. It's a great pleasure to have one of the greatest algebraists and computer scientists of our times. Little introduction: Professor Voevodsky graduated from Moscow State University, then went to Harvard in a flash. Defended his PhD, and now he's a full professor at the Institute of Advanced Studies in Princeton. As you know, a very prestigious institution with a few permanent faculty. We'll have about 50 minutes of discussions, questions, and then maybe 10-15 minutes open for questions from let's start with your previous life in algebraic geometry, where you push to perfection a trend which probably is not well known to our undergraduate students, definitely very known to the professional mathematician. And I'll give a few examples. For the last, let's say, 100 years, mathematicians were able to transcend the level of a theory and arrange their objects and entities in different structures. And for instance, we have the group of divisors, we have the ring of representations of a group, we have the semi-group of vector bundles, and we have the ring of quadratic forms and so on. This can go on and on. And you pushed, as I said, to perfection this mechanism. Can you comment a little about the roots of this idea and the future?
I'm not sure about the roots of this idea because I'm not actually all that versed in the history of mathematical ideas. It actually more relates to the second half of our conversation than to the first one, because it relates more to the work I'm doing now on new foundations of mathematics than probably to my original work on motivic stuff. And but it is indeed, I can only say that you're right. It is indeed true that a lot of achievements in contemporary or like 20th century mathematics came from considering, instead of individual objects, the collections of all similar objects and making this collection into a structure and then studying an individual object from knowing its relation to other objects of its structure. In fact, one of the key problems with set theory, which we'll get to in due time, I'm sure, is that typically a collection of, it's a typical mathematical object of early 20th century would itself be a set. Like, a typical object would be, for example, a finite group. So it would be a set with a structure. But then the collection of all such objects, like collection of all finite groups, for example, is not really anymore a set. Because it doesn't make much sense to say that two finite groups are equal. Like, suppose if I'm, what does it mean? Like, are two any groups with one element equal or not? Yes, they are, but like, are any two groups with three elements equal? Yes, in a sense there are, but they can be equal in two different ways to each other. So I think I'm jumping ahead.
No, that's fine. It's all right.
Because a group with three elements has an automorphism. So if I have two different groups with three elements, then there are like two different ways of saying that they're equal. And so the groups, finite groups, don't form a set actually. They form some more complex structure. And this is one of the main problems with set theory. And that we'll talk about later.
Thank you very much. Now going back to what you hinted, the next step, the current research you are doing, you switch quite fast, and I would say dramatically, from algebraic geometry to the foundation, to univalent foundation, how you call them. And I can see many examples, and I'll give a few famous ones. For instance, René Thom, after he did cobordism, he switched completely. Or Sergei Novikov, he did algebraic topology and then went into physics. Do you consider this change definitive, or you will return with new insights into algebraic geometry?
Well, I don't know if I'll return to algebraic geometry. This sounds... I wouldn't think it to be very probable. I may still return to doing some other mathematics in the way mathematicians do mathematics, so for the fun of proving conjectures or building theories, as opposed to what I'm doing right now, which is a very applied, in a sense, thing. And I'm trying to create a system which all mathematicians could use to do their work. So this is the goal. The goal is to create some software which, like every one of us, could use to make our lives simpler in terms of to remove uncertainty from our work, and to make the proofs which we create to be verified at every step of their construction. So in that sense, but I do have some backlog of things which I have started but haven't finished. One of the reasons being precisely that the constructions are kind of too complicated for me to be certain that I don't make a mistake. At the same time, I'm also kind of learned to be rather skeptical about the referee's ability to find mistakes in complicated constructions. So I have this backlog, and I can get back to it when I do have this software tools, and when I can then do my own mathematics using the tools which will develop.
Yeah, thank you very much. So the word univalent was used before for functions, or was used in different terminology. Why univalent foundations?
Well, there is a story behind it. So first of all, the univalent functions, I guess, in complex analysis, right?
Yes.
That's a different use of the term univalent. I don't think they are a little related, but not much. So the story was like as follows. So I needed to. So there is a notion of universal vibration, for example. Right? It's a vibration or universal object. It's an object from which every object of the same type can be obtained by a certain construction, and also in a unique way. So, for example, universal vibration is such a vibration that any other one can be obtained from it by pullback along a unique map, like universal curve and so on. So in this notion of universal, there are two components. One is that every can be obtained, and the second one in a unique way. Now, if you drop the condition in a unique way, then you get something which is called in algebraic geometry sometimes versal vibration. So it would be, for example, it would be a curve over a base such that every curve can be found in this family, but maybe several times. That would be called versal family. Not universal, but versal. So I needed something for which it would be true that everything which occurs there occurs only once, but not necessarily everything occurs. So it would be the other half of the universal, right? So the universal, versal is when everything, but maybe several times. And I needed something else. Not everything, but if anything occurs, then it occurs no more than once. And I called it univalent. Now, so the original term was for univalent vibration. It's a vibration where all the fibers are different. So if something occurs as a fiber, then it only can occur as a fiber once. So now the reason for the choice of the word univalent, I didn't know about this word. I didn't know about its use in complex analysis. I learned about it later. But there was a Russian translation of the Boardman and Fogg book on homotopy invariant structures. And in that translation, what we call faithful functors in English were translated as univalent functors. Why they translated faithful as univalent, I have no idea. But for some reason they did. And I didn't even know about it. So I read this book when I was just learning mathematics many years ago. And so I remembered this word univalent. And so I took this word univalent for this, first for this notion of only once, fiber occurring only once, and then for the foundations of mathematics, which came out of it. And I didn't even know that the original meaning of this word is faithful. So one can also translate univalent foundation as faithful foundations of mathematics.
This sounds more spiritual. Thank you. Now, speaking about fibrations and all the algebraic geometry, I'd like to go a little back and explain to the whole audience that you did fantastic work by resurrecting the ideas of Alexander Grothendieck, the motivic cohomology, and at a time when his insights were little put aside. I know the US environment, and Professor Voevodsky pushed this to a very high level, and he solved a series of long-standing open questions using homotopy theory arguments in algebraic geometry, and behind all this is the idea of cohomology. Can you explain a little, again, the evolution and maybe the future of Grothendieck's insight and your contributions for, let's say, undergraduate students who are here?
Well, which of the Grothendieck insights? Because he had many. In fact, univalent foundations are based on two main ideas, and one of these main ideas goes back to Grothendieck. It's the Grothendieck conjecture, as it was originally, that that the world of homotopy types is the same as the world of infinity groupoids. He conjectured it in his Esquisse d'un Programme in early 80s. But if we're speaking about his insights related to motives, well, the theory of motivic stuff is very complicated, because Grothendieck, when he was thinking about motives, it's very, very far from what people now understand. I mean, it's not very far. It's a kind of a peculiar part of a much bigger field which people now understand under the word motives. And actually, none of his original conjectures have been proved yet. And no one actually has the slightest idea about how to prove them. In fact, it's not that the conjectures haven't been proved, it's that since a long time ago, not a single non-trivial case of these conjectures have been proved. And how it's going to develop, I have no idea. But his other insight, this correspondence between this infinity groupoids and homotopy types, that's something which is at the heart of the univalent foundations, and that's by some coincidence of fate. This conjecture was originally proved by Misha Kapranov and myself. It was one of my first published papers, the correspondence between homotopy types and infinity groupoids, and the fact that it comes up again after 20 years of my work on something entirely unrelated to this is quite remarkable.
Yeah, it is indeed. Do you consider that homotopy theory is fundamental, let's say as fundamental as set theory, and we should expose all our students to the basic ideas of homotopy.
It does seem to be so. I would even say it's as fundamental as arithmetic.
As fundamental as arithmetic. So something for everybody here to...
It does really seem to be so. That it is some sort of... It's at the heart of the correspondence between geometry and algebra. Like if one tries to find something which really is in the center is homotopy theory. Because if you take, as I like to explain to people who don't have the slightest idea what homotopy theory is, one can explain it like that. So there is this, somebody's classic now this explanation, quote unquote, of what topology is. That topology is the study of essential properties of geometric objects. Like one takes a geometric object, one kind of abstracts away everything which is not essential, in quotes, about it, and then what one gets is its topological type, the type of the homeomorphism. So for example, like, I don't know, a sphere of, two spheres of different diameters will be different as geometric objects, but will do the same topology. So one can say that, so like the topological type of a geometric object is the essence of the geometric object, in a sense. So then the homotopy type is the essence of the geometric object. That's what it is. So then you first get the topological type, then you remove all non-essential things from the topological type, you arrive to the homotopy type. And then, remarkably, it turns out that the homotopy types now of sensible geometric shapes are themselves sensible objects which can be described now algebraically using only finitely many kind of finitely many words, roughly speaking.
We relate geometry to homotopy. Of course, we have the spatial intuition, and we do at least mental operations with shapes. And if we go back again about 140 years, Felix Klein said that geometry is the study of invariance of a group of motions. This doesn't hold more exactly in the strict sense for homotopy theory.
No, it doesn't.
So it's a big departure from the Klein point of view. Is there an analog? Of course, the group is too big, but another structure which replaces the group of transformations.
I'm not sure what to say about it. I was never particularly enthusiastic about this Klein's statement because it clearly only applies to homogeneous spaces, right?
Fair enough, yes.
And the world is not homogeneous. In fact, I'm generally rather skeptical about the ideas of symmetry because I really don't. I mean, they're nice when one needs to simplify things. I mean, by assuming more and more symmetry, one gets to more and more tractable objects. But when one tries to get to the more realistic worldview, the symmetries start to disappear. And if you look at this room and consider it as a geometric object, for example, just the surfaces, like the surfaces between air and non-air, then this geometric object has totally no symmetries. Nevertheless, it has a lot of structure. So similar to that, in my view, well, I mean, I don't know if similar to that or not, but one can even consider this as a homotopy theoretical object. If one thinks about it as a three-dimensional, as a piece of a three-dimensional space with a lot of the complement to the hard objects in the air will form a rather non-trivially complicated homotopy theoretical object, but again without symmetries. So symmetries, I'm not very high on symmetries.
Of of course, we simplify. Did you talk to physicists about this?
No, I'm waiting for them to discover it for themselves.
Now, on the same ground, we talked a little about set theory and what is now under construction and the very exciting work you are doing. Do you accept the real line as the physicists and the geometers using it?
That's a good question. Let's just replace the word accept by something else. But basically, I don't think that the real line is. Let's see. I don't know how to. I have a hope. Let's put it this way. I have a hope that there is a different and more adequate formalization of the notion of continuity than the one which is produced by the real line. And but that may really require. There are some really exciting ideas related to this and connected with the constructive mathematics, because the formalization of mathematics which comes up in the New Wayland foundations is inherently constructive, despite the fact that one can very easily formalize their very abstract mathematical objects. All this formalization of very abstract objects, such as n categories, homotopy types, and so on, turns out to be naturally constructive. So it's very natural to do constructive mathematics in New Wayland foundations. Now, when one starts looking at the definition of real numbers from the constructive point of view, it becomes very, very unnatural. And what is the correct definition of real numbers in constructive mathematics is an open question. And that's a little bit of a wild hope, but one of the wild ideas is that if we find a good constructive definition of real numbers, it might be very complicated at the end. But that might actually open up some new ideas into how to deal with all these problems which physicists encounter. Because they constantly encounter the problem that the equality of real numbers is such a nasty property. Because the equality of two real numbers requires verification of infinite amount of information. So equality of real numbers are very, very rarely equal. Like, in practice, it's impossible to check that two real numbers are equal. And that seems to be very related to all these issues of divergence of various series in things like field series. Because the whole issue there is also the fact that, like, if you have two particles in three-dimensional space, then and they fly, then they never. The trajectories never intersect. The space of lines which have an intersection have a measure 0, right? So that's the reason why the string theory works. It's a very, very simple reason why string theory works. Because if instead of points you consider circles, then if two circles are flying, then the probability that the corresponding cylinders that the space of paths of circles which have non-trivial intersection now has measure greater than 0, and now you can integrate. And that's basically my understanding is that this is the key reason why string theory is better than the classical theory, precisely because the reason that it boils down to the fact that the two real numbers almost never equal. So I hope that there are some new discoveries in that direction, but it's. I tried, of course, to think about it, and I didn't come up with anything interesting. But it feels very, very intriguing.
It looks like, and we wish you big success.
Thank you.
Now, you of course mentioned the real numbers and infinitely many operations. Do you believe in infinity?
I don't think it's a grammatically correct question. It's not entirely clear what it would mean. As you might have heard, I once gave a talk which was called "What if the foundations of contemporary mathematics are inconsistent?" And there I mentioned that it is entirely possible, and maybe even plausible, that something like Peano arithmetic is actually inconsistent. Because it's impossible to prove that it's consistent. That has been shown by Gödel. Without assuming something else, which would be equally impossible to prove. Now what one can ask is, do I believe that Peano arithmetic is consistent? That is something which one actually has to believe into, because it's provably unprovable. So it's even so one can either believe that it's consistent, or one can believe that it's inconsistent, or one can take a agnostic point of view and say that let's assume for now that it's consistent and try to work with it, but keep our sort of but let's try to do things in such a way that if it suddenly turns out to be inconsistent, that not everything which we have done falls apart. Which is basically the point of view which I am taking. And that's like, so one should, that's where constructive mathematics actually comes in very handy, because if one does something constructively, then even if it turns out later that the Peano arithmetic is inconsistent, the construction itself remains. Like if I write an algorithm to compute certain quantity, then the worst which can happen is that this algorithm will turn out to be non-terminating for some special values of input. But the algorithm itself will remain. So that's why I also think that we should kind of keep this little bit of doubt somewhere alive, that maybe it's inconsistent.
Thank you. That's very important for all to keep in mind. Now, speaking about your approach to mathematics, you mentioned constructivist ideas and on the algorithmic side. Do you consider yourself a constructivist?
No, I don't consider myself a constructivist. I certainly all my life worked with normal mathematics, not constructive mathematics, so a constructivist for normal. But it's just that as it happens that in univalent foundations, it's very natural to develop them constructively for as long as it doesn't prevent doing something important. But ultimately, I got much more sympathetic and much more interested in constructive mathematics over the last 2 years, but I still consider myself to be a classical mathematician in that sense.
So are you more a formalist or a Platonist or
pragmatic?
Pragmatic. That's very unusual for an algebraist. Very powerful, this combination of pragmatism and algebra. Now, speaking about your evolution and formation, tell us a little about your mentors and people who inspired you, and the Moscow school, the American school.
Well, let's see, that's a good question. So, there are several people, 3 or 4, will come together, whom I kind of consider as to have had a singular impact on my mathematical development. And the first was, the first person, his name is, just a moment, that was a long time ago, Oleg Sheremetyev. And I have no idea where he is now and what he's doing now. And at that time he was a student, undergrad student at Moscow University, and I was a school kid. And he was the one who once, we were like interacting somewhat and spoke about mathematics, and I was reading some books about mathematics at that time, and then he made this, and I told him that I'm reading this, and I don't quite remember what this was, and he said, well, like, man, what have you chosen? Like, are you crazy? You might have as well have chosen Bourbaki. And that was like, from his point of view, like the worst choice I could have possibly made. And of course, the next thing I did, the next day I went to a bookstore and found Bourbaki and started to read it, and I was really hooked, because I learned my original algebra and topology from Bourbaki. So, but Oleg was also the person who showed me for the first time what abstract mathematics is about. And then there was Yura Shabat, and that person, he's still working as a mathematician and still teaching students, especially undergrads.
Is he the son of Boris Shabat?
Yes, he's the son of Shabat from complex analysis, and with whom I wrote my first published paper. Then, and we worked a lot together, and he was my kind of first mentor who actually showed me how to do mathematics as a profession as opposed to as a study subject. And then there was Misha Kapranov, whom probably already kind of who is even more known. He's last I met him, he was chairman of math department in Yale, but I'm not sure where he is now. And we did a lot of very, very fun work on category theory, which is actually now, which has a lot of impact of what I'm doing now with univariate foundations, because this is in a sense what works out now in this univariate foundations is something which we dreamed about back then in like 1989, 1988 with Misha Kapranov, but we didn't know how to do it. And now it kind of comes together. So let's see who were Oleg, Yura, Misha Kapranov, and then there were, and then I would name Andrei Suslin, and that's the person with whom I did a lot of work on Mativik stuff. And of course, I learned a lot from him. He's a great algebraist and a very, very famous person. So I probably would name those four as those who contribute. It's those who kind of were most influential in my mathematical life.
Speaking about them, is there a Russian way to do mathematics?
Well, by the way, all four of them were Russians. So I don't think there's a Russian way of doing mathematics. I wouldn't buy them that.
No, if we look back, of course, there is a whole transition from the German, let's say, idealism to the French rationalism and criticism. And I would say the Russians are more mystic, and now the Americans are more pragmatic. With the British, we can play a lot. Now you are in the United States and you cannot say bad words about a culture or another, but the truth is we are here in Singapore, a new country, a new university, at the crossroads of old cultures, with China, India, Indochina, and we import in this very place ideas from the West. And how do you see the 21st century from this point of view of mathematics as a social activity and not necessarily geographical but more cultural?
I don't think that I see it in any way. I mean, I don't have a clear feeling of how it's going to develop. It's not that I don't really know. I think, I don't know how this univariate stuff is going to, how fast it's going to become widespread. And I think this is, from my point of view, this is a determining factor in how fast the changes which I see will occur. I mean, the changes which I see look approximately as follows. So that this computer software for for doing mathematics will become more and more widespread, for doing abstract mathematics. With the spread of this computer software, one of the things which it enables is the creation of big groups working on the same subject. Because right now it's almost totally impossible, because suppose I want to prove a theorem, suppose I make a group of 10 people and we try to work on it together, then who is going to verify everything which every one of these 10 people does? And if we want to rely on it and build a proof together, then everyone has to be absolutely reliable, right? Mm-hmm. Because one mistake and everybody will start building on top of this mistake, and the whole thing will not work. So right now, from my point of view, the main reason why mathematicians mostly work either in very small groups or individually is the fact that in bigger groups, the probability of one making a mistake, which everybody else will then build on, increases exponentially. So I think that's, in essence, that's the main reason.
And you imply then that the engineers make more mistakes?
No, but in engineering, I think it's easier to verify. It's more, I don't really know exactly how it works, but they either, I mean, nowadays they work with computers, so I suppose when an engineering task is done, to verify that it has been done correct is easier than to do it again. In mathematics, it's often the case, and to verify a proof is actually more complex than to invent a proof anew, especially for a relatively simple statement.
That's very true.
So my vision is that eventually, as this software for doing mathematics becomes more widespread, mathematics will, the culture of doing mathematics will change dramatically in terms of there being bigger groups, and mathematicians will, that's my dream is that, as I was saying, that the pure mathematicians work with objects of high abstraction and low complexity. Low complexity is what mathematicians call elegant. So applied mathematicians work with objects of low abstraction but high complexity, like a lot of variables, a lot of stuff. Now, to bridge pure and applied mathematics, we need to learn how to work with objects of high abstraction and high complexity. Now, the reason why nobody does it is because it's extremely complicated. And again, the probability of mistakes is very high. So my dream is that when we get this software, which will provide a much kind of more reliable way of doing abstract mathematics, we'll move into this now closed for us area of objects of high complexity and high abstraction, and that will kind of move mathematics on the next level of development.
That sounds very interesting. And related to this, just to close the circle of ideas, we live one of the biggest revolutions after, say, Gutenberg, the internet. And we have all problems of stability, of security, and all computer science related to it. Do you think that the univalent foundations will impact the internet in a near future?
Well, not univalent foundations per se, but this field is very much interacting with the field of computer languages, of formal deduction systems, of semantics of computer languages. So it very much both takes from that field, and also I think eventually will start giving to that field. So through that field, through the semantics of languages, there may be eventually also impact. Well, the people with whom I'm working are very, very closely working with people who are doing software verification, for example. Software verification, I think, is an extremely important thing, because especially as software will be moving into more and more of kind of crucial applications, the verification is a very important thing. And software verification and theory of languages excuse me, software verification and proof verification are two subjects which historically developed almost indistinguishably from another. They're the same people working there. So there will be some connection, but I'm not ready to speculate about what kind.
Thank you. And we are almost there. A couple of questions. What advice you would give to our brilliant students here who have the gift for mathematics and the fire from inside?
To look into proof verification? Because I think that in the future it will be, I think it's the future, in a sense. So,
you made a strong point, and I think they will carry on the message. And the last question, besides mathematics, what are your hobbies? What is your pastime?
Oh, my pastime when I have enough energy left is reading, definitely. And, well, other than, well, yeah, for most part. And I'm an extremely curious person about how the world in general is functioning. So I'm learning a lot about history, religion, stuff like this. But it's a topic for a whole other conversation.
Thank you very much, Professor.
Thank you.
We have a few minutes for questions.
Sergei Duzhin, a visiting professor from St. Petersburg. So you said that the probability that two real numbers are equal is 0, but the probability that two lines in 3 space intersect is positive. Can you comment on that?
No, that's not what I said. I said the probability that two lines in 3 space intersect is 0, but suppose so a line is the path of a point, right? So, but suppose instead of a point you consider a small circle, and you take a path of a small circle, it will be a cylinder in space.
Okay, I see.
And probability that two cylinders intersect is greater than 0.
Okay.
And so replacing points by circles, which string theory does, takes you out of this problem.
More questions?
I'm Etienne de Klerk. I work at the mathematics division here. So I have a philosophical question. You said at the beginning of the interview that you are developing proof verification software to help the mathematicians in their daily work. But I once saw a formal proof of the Jordan curve theorem, and it was thousands of lines of computer-generated text, and the layman could not even recognize this was a mathematical proof. So this is something very different from the kind of mathematics that practitioners are using. So you have the kind of human mathematics, and you have the formal proofs, computer-generated mathematics. So how do you see this brave new world where one part of mathematics is a human activity and another part is more a computerized activity?
No, it was just a very bad computer proof. Honestly, I mean, it was using a language which was not adequate for the task. I mean, Tom Hales, who did it, he's a real pioneer, and as many real pioneers, he was like really ahead of time. And when he started working on that, there were simply no languages in which to formalize interesting mathematics. And he took one of the languages which was not adapted for that, and did heroic work by proving something in real mathematics using a totally inadequate language. And that's precisely what Univan foundations are about. It's about foundations of mathematics which can be formalized in a language which is actually readable and understandable by a normal mathematician. So like a proof of, I didn't do a Jordan curve theorem, somehow I wasn't much interested in it, but a proof of many, I have some library of formalized mathematics in Clock. That's a proof of system developed by French guys, and it's totally readable. When someone now, I also have some grad students who work on formalizing other parts of mathematics, and they send me email with this formalized proof. I look through it, I can read it quite easily.
Thank you. Any more questions?
What do you think are the very important problems to solve in the point of view of mathematicians, include very complex, which include complexity and very complicated rules?
You mean high complexity, high abstraction?
Abstraction.
I don't know yet. I mean, that's a kind of theory incognita in a large part in mathematics. We will be moving there slowly. I don't have any examples, and because it should be high complexity, it wouldn't be elegant in a sense. It wouldn't be something which I could explain in 2 words in a microphone. But I answer is I don't know yet. I mean.
More questions?
So you're working on making computers understand proofs and verify proofs. So then, do you think that it will be possible to make computers mimic proofs and produce proofs in the future?
Well, it's so the answer is to some extent yes. And also when one actually works with modern proof assistants, when suppose I want to prove a lemma, right? I don't really write down every single tiny step of the proof by hand. That's not how they work. They work through something which is called tactics. And so there is a collection of these programs which are called tactics with different names. And so you have this statement of a lemma, and then the system shows you how it looks and what you really have to. System just shows you this statement in the formal form. And then you basically, the way you interact with the computer is, you prove it interactively. The way you do it, you say, try this tactic on this goal. And the system tries it and shows you what happened to the goal. And then you see whether it actually what you wanted to get or not. And then if it is, you give it the next tactic. If it's not, it says you try another tactic. So the actual proof, the proofs actually are physically much shorter than the same proof would be written by a human. I mean, for reasonable statements. And I mean, if the proof of a human would be very detailed, it would be longer. But they're shorter than proofs written in normal language, and they just consist of this sequence of suggested tactics. So it basically says, so the proof is a sequence of this hints to the computer of what to do. And each hint, when it gets a hint and tries to apply it to the goal, it actually sort of does create a small piece of a proof. And so some tactics are more advanced than others, and there are some very complicated tactics which may take longer to run, but which may get you sometimes you can get the whole proof in one tactic. So in practice, any proof assistant in practice does invent some short stretches of proofs.
Behzad Hashim, undergraduate student. I heard that you don't have a bachelor's degree in mathematics, but you are one of the most famous mathematicians of the world. Does having a degree in mathematics, is degree in mathematics not a prerequisite to become a famous mathematician?
Is degree of mathematics is what?
Like prerequisite to become a good mathematician? I mean, is it a necessary condition?
I don't know. But I do have a PhD though, and if I didn't have a PhD, it would be very difficult for me to be a professional mathematician. So, and also the reason I don't have BA is that, well, I mean, it would be, one of the reasons why I don't have it is because when I was as an undergrad in Moscow, it was the time when the Soviet Union was kind of collapsing, and so everything was kind of very shaky, and it was really possible to go to Harvard without having a BA, Harvard grad school without having a BA, because they were kind of very considerate of the problems of falling apart Soviet Union. Today it might be more difficult, but on the other hand, I'm not saying that it's necessary to have a degree. But it's definitely more convenient to
Thank you. More questions?
Daniel Moskovich, research fellow in mathematics. So I want to know if you think that n categories are a fundamental notion at the basis of mathematics, or whether we're moving towards something more inherently high-dimensional, like modular operands, or something that's actually sort of in a plane as opposed to strings.
So the first answer is as follows. As far as I understand, categories, n categories, or even usual categories, are not that fundamental. What are fundamental are n group weights. So n group weights are definitely fundamental. And for example, usual group weights are more fundamental than categories. So the correct way of thinking is that a group weight is like a higher set. Is the next level set, is not a category. The next level set is a group weight. A category is the next level partially ordered set. So n categories are something like partially ordered n sets, which might be fundamental or not so fundamental, but n sets themselves are n group weights. As far as for high operands, I don't really know. I'm actually going to learn about high operands in the next few months, because I somehow skipped this part of mathematics over the last few years.
Thank you. Please join me in thanking Professor Voevodsky again.
Thank you.